to figure it out. So now looking at the next example, the first question is, do we have any difference in our carbon backbone? So the answer to this one is, we don't. We have the same amount of carbons in our starting material and our final product. So we don't have any change in our carbon backbone. Carbon 4 still has 2 CH3 groups attached. We still only have a total of 7 carbons. So we're not changing anything about the amount of carbons in this case. So we won't be forming a new carbon-carbon bond. We do have differences though. On carbon 2, in our starting material, our functionality is on carbon 2. We have a bromine. That's a good leaving group. And in our final product, we have a carbon-oxygen double bond on carbon 1. So I'm going to go through the best route. I'm not saying this is the only route. There are other routes you can go through, and especially as we start going through more examples and going through more reactions, there's going to be multiple ways to work synthesis. And that's always true. There may be a better way. Sometimes there'll be multiple ways that are equally going to give you, or at least theoretically going to give you close to the same yields. The best way is typically a route that's shorter, though if it's the difference between 3 steps and 4 steps, it's not that different. The difference between 3 steps and 20 steps, 3 steps is better. Every step you're going to lose compound when you try to work it out and separate it. Your better synthesis are usually ones where you don't have a lot of byproducts. So if you don't have, let's say, regioselectivity, and there's a route you can go through where you do, that would be a better route. But in some cases, there's multiple routes. In this case, the route I'm going to go through is probably the best route, but there is actually another route you could go through to get this, but you'd get more byproducts through that route. So one route we can do is, you notice we formed the carbon-oxygen double bond, and there's only 2 reactions we've talked about. One is reacting a triple bond with our hydration, which will form our carbon-oxygen double bond because the enolate isn't isolatable. So you should recognize that at this point. Later on, we're going to talk about multiple ways to form a carbon-oxygen double bond, especially in chapter 13. But as of now, we've only really talked about 2 ways. So we can do hydration of a double bond, and of course our intermediate is that enol, but we're going to isolate the ketone or the aldehyde. Depending on which carbon it adds on, it's going to be more carbon-carbon or anti-carbon. Our other route we've talked about is ozonolysis of a double bond. Now, not of a triple bond. Why not? What is your product for ozonolysis of a triple bond? How many oxygens are we adding to the pi bond on the double bond? 1 on each carbon. With the triple bond, how many oxygens can we add? 2. So with the triple bond, you don't isolate aldehydes and ketones. You isolate what? Your carboxylic acids. You must know this because I'm going to test you on it. Because we get 2 additions. Because we have 2 pi bonds. So we don't have a carboxylic acid. So we can't go through a triple bond. The problem with going through a double bond is we fully break our bond. And the amount of carbons we started with is the amount of carbons we finished with. So unless if we add another carbon, carbon and then do Oh's analysis, which we could, but that'll give us extra steps. That's not the best route. Does everyone see why? If we break the bond between carbon 1 and carbon 2, we're going to have less carbons in our final product. So the best route is going to be this one, based on what we know so far. Which carbons does that triple bond need to be on? Between? One and two. Now, if I just add NH2 minus to our starting material, will I get a triple bond? No, why? Why wouldn't I get a triple bond if I added my strong base to my starting material? What do I need to form a triple bond? We have a strong base. What happens when I form a triple bond? How many bonds? You need 2 leaving groups, and you need 2 hydrogens to deprotonate. Because remember, here's our carbon of our single bond. Here's our double bond. What's the difference with the amount of hydrogens? If a carbon is participating in a triple bond, how many groups can be attached to the carbon besides the triple bond? Just 1. I need 2 leaving groups. I need to make room for that bonding. If I don't have 2 leaving groups, if I don't have 2 beta hydrogens, then I'm going to have too many bonds to my carbon. So I only have 1 leaving group. I got to get 2 leaving groups that I can form the triple bond. So we can do that. We can do that by forming a double bond and then doing our Br2 reaction. But our double bond needs to be between carbons 1 and 2. So that's our least substituted. Now that we have our double bond between 1 and 2, we can put our 2 leaving groups on that compound. And this is the best route that we have to put on our 2 leaving groups. Of course, we'll get both enantiomers, but that's kind of irrelevant. They'll both form the same triple bond. For the elimination? No. If you have this reaction with H3O+, your pi bond is going to react with the hydrogen, and then the alcohol will attack. Now, you might take some of this, but you'll probably get a big mixture of things. And if you do this reaction in water or alcohol as a solvent, then instead of having 2 leaving groups, your water or your alcohol will attack after you form the ammonium ion, because you have a lot more solvent. That's why we use CCl4. It's non-nucleophilic. It doesn't have a lone pair that's available to attack the chlorines or stable, because they already have their 1 bond and they're full octet. Carbon doesn't have any lone pairs, so it's non-nucleophilic. If you do this in the presence of water or alcohol, then that's a nucleophile, and once you form the ammonium ion, you have so much of that water and so much of that alcohol that it'll attack. So you got to be careful with that conditions. So this will form your 2 bromines. Now we have 2 leaving groups, so we can form our triple bond. And again, we're going to use an excess of our strong base, followed by water, because we do want to isolate this triple bond. And I'm putting my numbers because I want to make sure I don't make a mistake. Especially when you draw a triple bond, it's easy to add too many carbons. For some reason, when students change the geometry and make it straight, they always end up adding too many carbons. So just count your carbons. You shouldn't have any more. So notice 1, 2, 3, 4, 5, 6. That's not right. I put too many. So numbering them, make sure you don't accidentally do that. Remember, each end of the triple bond is a carbon. I keep on doing it. This is carbon 5. Carbon 4 still has 2 CH3 groups attached. So now 1, 2, 3, 4, 5. So I have my right amount of carbons. So watch your carbons. It's easy, especially with the triple bonds. Something about changing the geometry confuses everyone. So if you're numbering them, you won't make a mistake. Now, I want to do my hydration, but I want my oxygen to add on carbon 1. So which reagents do I need for that? Is this Markovnikov or anti-Markovnikov? It's anti, so which reagents do we use? Our boron. Now we do not just want to use BH3THF because we get byproducts that way, so we want to use our R2BH followed by our peroxide and sodium hydroxide. In the book, a common one is the 9BBN. That's fine. That's just a specific R group. Or you can write R2BH. I'm okay with that as well. There's another one that they put in the book, the diisoane. I don't know whichever one. You can draw it. It doesn't matter as long as you're clear that there's 2 R groups of boron. Also note this is a 1 and a 2. We can't mix water with our strong base. Our strong base would just react with water before we react with our alkyne. This is the pKa of this hydrogen. I don't know exactly what it is. It's a little bit lower because it's a leaving group. So the boron's electronegative, so it makes the pKa smaller. But it's not 60. It's not as low as 60. And the pK of this hydrogen is 15.7. So the strong base will react with water before it react with this. So we have to make sure that the water's added second. You can't do a reaction in water with a base that's stronger than OH minus because the equilibrium will always lie towards the OH minus instead of the NH2 minus. So you got to be careful with that. And that's explained in chapter 3, so you can go back and review that. So that synthesis is pretty straightforward. The other synthesis that you could do, utilizing this, would involve you, once you get here, because you need the triple bond, you can, let's say, add a methyl CH3, adding a new carbon, there we go. I'm just going to write CH3. And then we can reduce that to the double bond. And it's irrelevant whether you form the cis or trans double bond in this case. Because it'll give you the cis or the trans will give you the same final product of what we're trying to do. And then we can do our ozonolysis. And when we do that, oh no, we still can't do that. We would then need to move the double bond over to between that NCH3 group. This isn't a good route. It's too much work. And then once we do that, we don't have any regioselectivity. So this isn't a good route. I kind of got myself stuck. Because I need the double bond here. So that way we break this bond. Then we form one compound that has this compound we're looking for, and then we're going to form formaldehyde. But to get the double bond here, we need our bromine to be here, and we don't have any regioselectivity because this and this has the same substitution. See how I made that really hard? You get to a route that's like this, it's not a good route. Erase it, start it over. This route is too complicated. And even if we did finally get to, which would be difficult because we wouldn't get a very high yield, even if we got to do our ozonolysis, we would still get that byproduct of formaldehyde, which could be problematic in our final separation. Because we'd have to separate formaldehyde out. But our big problem is going to be the control of moving this double bond between 1 and 2 to between here. Because we don't have any selectivity between carbons 1 or carbon 2 for adding our halogen. Not a good route. The first route is a good route. This route, not a good route. I'm not saying you wouldn't form any of your desired product. It would be a low yield and it would be a pain to separate these things in the lab. So not a very good route. And this would take 2 reactions. So this route here is the best route based on what we know so far. Like I said, there'll be multiple routes to form our C-double bond O later on. But based on what we know now, this is the best route. Now, if you look at this one, it's always a really good job, or makes it easier, to figure out where in your final product your carbons are. Well, we're starting with a completely unsubstituted triple bond. And we don't exactly know which 2 carbons were our original 2 carbons. And I'm going to go through the simplest route for this. But there are multiple ways you can do it, and it would still lead to a final product. But there's one way that you can't do it, and that is your triple bond, we call this 1 and 2, cannot be these 2. Why can't this be carbon 2? So if we were trying to, if we called that carbon 1 and 2, we're forming a new carbon-carbon bond between carbons 2 and 3, correct? So that would mean we're taking carbon 1 and 2. And the only way we learned how to do this is by doing what? Deprotonating it. And then reacting it with an alkyl halide, correct? But what are our limitations for our alkyl halide? We have to have a leaving group. Where would my leaving group be? Which carbon? Carbon 3, right? Oh, sorry. Sometimes the system does weird things. It keeps on doing it. No color coding, sorry. What's wrong with that? What's our limitations for our alkyl halides? Has to be primary. What is this alkyl halide? Secondary. So this route won't work. That won't lead to our final product. Instead, what are we going to form? We're going to reform our triple bond. And what reaction is going to occur with the alkyl halide? We can't do an SN2 with this secondary because there's another reaction, a competing reaction that's going to happen faster. E2. So instead we're going to form our triple bond and reform and form this elimination. That's not our final product, so that can't be our triple bond. Because our limitation is our alkyl halide has to be primary. Does everyone see that? So that can't be our triple bond. The easiest route is to call this 1 and 2. And this will be our new carbon-carbon bond. So we can deprotonate and our alkyl halide is going to contain the rest of these. And where is our leaving group going to be? Carbon 3. And is this primary? It's primary, so we can continue. So remember, we're going to retain our triple bond when we do this reaction. But we're going to get our new bond and the rest of the carbons. 3, 4, 5, 6. So this isn't our final product, but it's pretty close. What do we have to do to get our final product? What's the difference between this intermediate product and our final product? We get rid of the triple bond. So what are we adding to the triple bond? Hydrogens. We're going from the triple bond all the way to the single bond, so we can just do this with H2 and platinum, palladium, or nickel. The other route you could take is to make this your starting triple bond, and you're just going to have to add this side and this side separate. Which you can do because it has 2 acidic hydrogens. But why, when you can just do it in one reaction? So it might be an issue of you don't have this alkyl halide in the lab, but you have the alkyl halide that contains this, and you have a methyl alkyl halide, then you might do the other route. So that would just be adding an extra step because you'd have to do the new carbon bond on both sides. But the first route that I showed can't be done because we won't get a high yield. You might get some, but you'll mostly get this. So this is the easiest option, but you could also make this your triple bond, and then you just have to add this side and this side to it. And think about doing that and drawing it on your own. But this is the most straightforward option. And remember, when you deprotonate your alkyne in an attacks in an SN2 reaction, the lone pair is what's forming the new bond. You're not doing anything to the triple bond until you react it, either by reducing it or reacting it with something else. So you're retaining it until you show the reaction occurring. Okay, and the last one, again here, we're starting with a triple bond, but there's only one route in this time. There's only one possibility of my carbons in my final product being my 2 carbons I started with. And again, that's because of that limitation of the fact that our alkyl halide has to be primary. So the only route in this case to do this is if I call this, and this 1 and 2 is irrelevant, this is just for me. If I call that 1 and 2, this must be 1 and 2. Because this carbon would be the only one that would be a primary alkyl halide. This clearly can't be the triple bond because this carbon has 2 R groups, so it can't form a triple bond. And then these are part of the ring. And we can't really have a triple bond in a 5-membered ring because first off it would be internal, and second, it has to be linear, and a 5-membered ring is has too much angle strength. So you won't typically see a triple bond in a 5-membered ring. So that's our only possibilities. So that means that this is going to be our new bond. And we're adding these carbons to it. So we can deprotonate our carbon 2. And again, it's kind of, I drew that 1 and that 2 for me. It doesn't really matter which side you deprotonate, it's going to lead to the same final product. So we want our strong base. Notice this is only 2 hydrogens because this is this. If it's NH3, then it's neutral. Remember your bonding patterns of nitrogen. So we have our strong base, and then we want to react it with our carbon-containing group. So our alkyl halide will be on carbon 3 because that's where our new bond is. And again, make sure you're not putting too many carbons. And this could be a chlorine, iodine, bromine. So the amount of carbons total of my starting material plus this should equal to my final carbons. So count your carbons. Make sure you're not adding too many. Carbon 3 is primary, which it needs to be, so we're good there. So that will form, and I'm just going to draw it in the same way that this is oriented. So I have the right amount of carbons, and I drew that correctly. Now our last step is fairly straightforward. We're forming CO bond O. Again, these are only 2 ways we talked about it, but based on what we have, this is the best route because we're not breaking. We have the same amount of carbons. So this is the best route, but the question is it Markovnikov or anti-Markovnikov? It's Markovnikov, so we're going to use our acid catalyzed hydration, our H2SO4 with H2O, and with the triple bond, we want to add our catalyst, which is our HGSO4. It just helps catalyze the reaction, otherwise it's just too slow to react. Because remember, a carbocation won't form on an sp2 carbon. So the HGSO4 changes the mechanism a bit because it stabilizes that carbocation by donating electrons to it. And you don't really need to have to draw that mechanism because when the mercury becomes involved, it becomes a little different. But that's our synthesis. So those are the 4 with that. And there's more, of course, in your homework, and I really suggest practicing. The biggest thing is you have to know your reagents. And then if you go through these steps of always analyzing the starting material in the product, trying to find where your starting material is in your product will help, what new bonds form, what changes between your starting material and your product, then the rest is just mapping it out and solving a puzzle. And it could be kind of fun if you like solving puzzles, but you have to know the reagents and what they do. In understanding reactivity, don't just try to memorize, but really think about, okay, I need a partial positive carbon so my nucleophile can attack. What do I need for that? I need a leaving group. Those kinds of things, if you understand that, you're not going to be memorizing a bunch. Any questions with these? All right, well, that's it for today. If there isn't any other questions.